Today I want to talk about somehow certain finiteness conditions you can impose on motivic sheaves or in general objects in some such six-function formalism. So I call this geometric, constructible, and compact objects. And these are the three possible finiteness conditions you can impose. And so my goal is to first define that and say something about how they relate. Right. So what do I want to begin with? Maybe I will slightly deviate from the thing here and rather begin with briefly recalling. I guess you all know it, but so what's the idea or the goal is? So we have this six-function formalism. So on some nice enough integral schemes, so let's say finite types over some space schemas, and so we have some scheme there x, and we look at d of x, right? We want to, like I said, we want to impose certain finiteness conditions on objects here. And the first thing is, so recall that there is no generalizability. So for the moment, I've looked at like C for any such a category. So if the C will be a preventable stable within category, so an object C and C is dualizable, even only if there exists some object C dual and an adjunction. So you take a functor given by tensor with C, and this is supposed to be left adjoint to the functor given by tensor even if there's other object C dual. So the unit map will be the evaluation, co-evaluation, and so on. Yeah. So that's that. And I like phrasing it that way, or generally speaking, I like phrasing all these finiteness conditions as far as possible in terms of such adjunctions, because I think that's kind of clarifying what's going on here in some sense. So that's one condition we can impose. And then of course we have a notion of compactness. So one notation, I will write C DBL for realizable objects. Yeah? So this is the full subcategory of realizable objects. And then, well, maybe this I don't have to recall that. Anyway, C is compact. If we give this mapping spectrum functor, maybe I'll just map in C from C blank. This is functor from C to spectra. Preserve splitter for limits or preserve all limits, which is equivalent in the context of a stable such category, stable presentable category. And again, it's I believe a good idea to phrase it in terms of injunction. So what is this functor here? This mapping spectrum functor is the right adjoint. So this is the right adjoint of what? Of the functor from spectra going to C that sends the sphere spectrum to that little object, little C. Yeah. So this right adjoint needs to be continuous. Yeah. And so we write C omega is little for the subcategory of compact objects. Okay, good. And in some sense, actually, that's a bad definition. I'm convinced, even though I'm not yet fully able to sort of use that conviction. So why is it? I mean, the bad definition, of course, in our context, let's say. So why do I consider it, in some sense, an unnatural definition? So you see, all we are trying to do is relate to this six-function formalism. So this category of spectra has, in some sense, nothing to do. We should even sort of let it enter into our little garden here. So and there is a variant of this. So a variant, which I think is useful to have seen once, and I want to present, even though not all that much was going to happen with it today, at least. is the following. So this is the notion of atomic object. So if you want to read up on this, I learned this from the work of Maxime Ramsey, pretty recent. So let A be a commutative algebra object in PRL. So this A will be our D of S in a moment. So thinking A is D of S. So this is our ground ring, quote unquote. and C, or no, I wrote M here, M a module over A again in PRL. Yeah, so the M will be D of X, where X is over S, and this D of S will act on here by tensoring with the upper star along this line. Yeah? So which is how I would consider the action here in a moment. So, but the difference here works in the generality. And so now we want to impose a finite estimate of objects in here, which somehow is rather taking this as the base ring in some sense. And so it's the definition. So an object M is called atomic, or maybe atomic if I want to emphasize it. If this functor it goes from A to M and is given by sending M little a to a tensor M, if this functor is the left adjoint, this is the left adjoint. Left adjoint within, and this is now the key part of the sentence here. Within what a so what do I mean by saying within? I mean, I don't want to spend too much ink here or chalk on infinity true categories, but what I'm really saying here is that i.e. the following. So both of A and M, they are both presentable, yeah, and this tensor functor is also going to be fully preserved by virtue of being the module in parallel. So this functor A tensor A goes to A tensor M. This always has a right adjoint. Has a right adjoint, which I call map M over A from M comma length. So this is a functor from M to A. Yeah. So from a module to the ground ring. So this is very similar to how you, let's say, if A was linear vector spaces and you want to understand how is it that, or why is it that the internal Hom is a vector space, well then you're simply talking about such an adjunction. Yeah? So anyway, it has a right adjoint. So the right adjoint here is for free. That is not a condition, but this right adjoint needs to be first of all the functor in PRL, i.e. Continuous. Okay, preserves coordinates. That's where is it? Let's sort of connect to that. But on top of this, it also needs to be linear. So it needs to be PRL and a linear. So being a right adjoint of some A linear functor is always lacks linear, and we insist on it being linear. So this is the equivalent to saying that so map of M maps from M to some A tensor M prime is maps from M to M prime. Again, this relative sense tensor with A. Yeah, so there's always a map going that way, and we want this to be classical. So these are the two conditions. Yeah, so there's and I think that's the actual sort of the correct definition that replaces compactness. So let me make a few remarks that relate to that.
The first condition isn't automatic, that it is continuous.
This one?
Yeah.
No,
because
it's
it
not.
it is a left adjoint.
Well, that is the right adjoint.
Yeah, I mean it has the right adjoint, and so it
preserves limits, not columns. Generally. So continuous means. Is it continuous? Yeah, I wrote continuous here. Continuous means.
Yes, is the right adjoint.
So this functor A going to A tensor N has a right adjoint.
Yeah, and
that right
you want the right adjoint to be okay.
Also a left adjoint.
Yeah.
Or also preserve columns.
Yeah. Okay.
So that is certainly not always going to be the case, as you can already see. I mean, where was it?
Yeah, sorry.
Where is the main house? Yeah. So
yeah, I got confused.
Yeah. So maybe let me write the functors again. So we have A to M. So this is basically M tensor plane. Okay. And this has a right adjoint, which is map M over A of M comma length. Okay. So that's the right adjoint of this. So this exists always because of preservability, but it might not be column preserving. I asked it to be column preserving. So if you wish, you can say there should be yet another right adjoint of that, which I prefer not to even think about. But yeah, that's an equivalent way of phrasing that condition. And that other condition is not strictly related to this, but rather it's like I said. So this one is alinear. So therefore this is automatically less alinear, which tells you have such a map here, and you want that to be less often as well. Okay.
Another question. In the
Yes.
of contact, don't we usually currently preserving filtered coordinate?
We do. So I think I said already. So I said here C is a stable category. If I drop that, then I have to say filtered. Exactly. Yeah. But if it's a stable category, then preserving filtered columns is equivalent to preserving all columns because finite columns are also limits, and that's why. Yeah. But right. So that's a little bit of a shortcut. Good. And you might have noticed here in this definition of atomicity, I didn't write clear stable just because it's not necessary. So actually, this definition is sensible and useful to apply beyond stable. But anyway, we will care about stable mostly. And so, what do I want to? I want to sort of relate this notion of being atomic a little bit more to not being compact. So, yeah, let's say remarks. So if A is, so there are three extreme cases. One is that A is just spectra. In this case, being spectra atomic is equivalent to being compact. Okay. So why is that? So this second condition here, the linearity, this turns out is automatically if this A is dualizable. Yeah. So A is dualizable, then this condition is automatic. So this one here, automatic, if A is dualizable, and since spectra are generated by the sphere spectrum, which is dualizable, but in that case, this is automatic. And the other condition is exactly what we had before. Yeah? So that's that. That's the one case, sort of the absolute base ring, if you wish. And what is another case worth looking at? So what happens if A is equal to N? Yeah. So in some sense, you ask, you ask, please be atomic with respect to yourself, then you can say A atomic is equivalent to being dualizable. Yeah. Okay, so in that sense, this being atomic equivalence between these two versions. And so in the case that we care about, which is this one, what can we say about this mapping, about this relative mapping guy here? So this has an explicit formula. So if A again is d of s, and M is d of x, and again this map here of f, then this relative mapping guy d of x relative to d of s is something concrete, namely this is F north star of the internal home upstairs on it. So you kind of ask you the internal home and then push forward how to your base scheme to be different conditions. So once again, the second part is automatically if A is going to be generated by dualizable objects, which will be the case often enough when as the spectrum will appear. So that will be a kind of that project. And then you ask this one to preserve colimits, which also will often be the case, namely when this first blank here is what's called constructible logic. So these are. So what I'm trying to say is this note of being atomic relates to other sort of other things here in this area. Okay, good. So, okay, but that said, I will phrase most of the results later on in terms of compact objects. But I think eventually that should be superseded by this being atomic thing. But anyway, good. Now, next step, or here's the first actual definition. So we fix our six functors formalism. So maybe I should say from now on, so we will fix the following. So S will be an Ethereum finite dimensional base scheme. Yeah. And we will consider T, which is the six functor formalism on, so we will consider scheme of finite type over S, or maybe also the schemes over S that are QC, QS, but then, well, we don't have all that much to say about exceptional functors, so let's say maybe then I'll just say D will be a contravariant functor from here to, again, see. Yeah, so we will, so this is the kind of thing that I will also say something about going back and forth between these. But anyway, so let's fix that. So the example, of course, we have in mind is SH with one of these topologies, especially with Snell et al. Actually. So almost all the interesting results that I'm going to make will only apply really to Misnevich or et al. As opposed to this Wheatley et al. Or Kronisnevich. So what is now in such a generality? I think what is the correct definition of a constructible object? So we want to mimic something that gets us back constructible sheaves in context of analytic sheaves. So here is the definition. So d cons of x, and x will be one of those best schemes. Yeah, so d cons is the full subcategory of d of x of the following form. Is the is the subcategory of objects of, let's say, f and d of x. That there exists a partition, so by which I mean S is theoretically the strong union of some locally closed subschemes W. So this is a finite partition. Yeah, actually it's a finite partition, and these things are locally closed subschemes, such that if you so well, if I write this here, maybe I shouldn't. Let me write S dagger for this really this disjoint union, which will map to S. Yeah, so I call this in iota. So a partition means it's, these are locally closed subschemes, but again, and the map is bijective, on the level of points. But of course not the way I want to. Anyway, so the condition is now that iota R star F is dualizable and I write S and X. All right, it's X. Such that iota R star F is on this X dagger after passing through stratification is dualizable. Yeah, that's the definition. And I call these constructible objects. And if this D was, like I said, the category of, for example, an Alex sheaf, then this would be exactly the notion that you are used to. So also very markers here. Example. So if this D is just D of X and QL, for example, then this is what's usually called DB constructible. So together with Timo, we have kind of studied this in quite some detail. That's the, I think, the correct definition of constructible object. And now there is another notion which also makes sense to consider, namely that call this T geometric, or geometric objects. So I keep changing X and S. So let me, yeah, I don't know. Okay, let me stick to the notes. So I mean, whatever, the S is not that S, but rather some. That's not great, but I'll try to put it in text. So GM of X, this is the full stable, idempotent, complete subcategory generated by what? By F lower shriek F upper star 1 with M, where M is in Z. So I rotate twist, and this F is, let's say, from T to X is finite. Is a map of finite type. So now I'm using that maybe so that I'm this context, yeah, so that all schemes are automatically Noetherian, and so all maps that are finite are also finally presented. So strictly speaking, that would be the condition that I would have to put in beyond this Noetherian case. But anyway. So basically, upper star, lower shriek of the monodal unit, and then all these twists. And I want to introduce a name for this here because it will come out wrong, and so I will call the motive, the Borel-Moore motive of T, or maybe T over X if I want to emphasize the base scheme here. This is just this F lower shriek and upper star one. Okay, so that is as opposed to the regular motive M of T, which would be F lower shriek F upper shriek of 1. So initially in the context of SH, we said the motive, we only defined motives for smooth things. So if indeed F is smooth and you have all this top stability and so on, then this will be F lower of 1 and upper star 1. Yeah, so that was the definition back then, and so this for a completely general 600 problems, I think it's wiser not to insist on this left germ because it doesn't exist always in the first place, and so that's the correct move in general. But here we will look at this variant, which is a little bit more somehow, yeah, nicer to play with. Okay, this is the geometric subcategory, and so I want to say D is geometrically generated. So this is my own little terminology here. If D of X is generated as a presentable category by this idempotent complete subcategory DGX. Yeah? So geometrically generated means all objects come from geometry in the sense of coming from basically finite type maps. Yeah, so the example to have in mind here is, of course, SH, for example. So SH is native and SH et al. They are geometrically generated, right? Why? Well, they are by definition they are defined by these kind of objects up to twists, yeah, for smoothness only, because that's what the site was about. And then you can you can replace it with that. And then we have seen that in that context, for a smooth map, upper star and upper tree are isomorphic up to this Tom twist, this what I call C of TF earlier. Maybe I wrote it down. So F smooth. Then we had seen that upper star tends to this C of TF that I defined. And if now this might be in general something, but if if you work locally on the T, then the tangent bundle will eventually be trivial, and so risk locally this will be trivial, and then you really a twist and shift. Yeah, and so that's sort of accounted for here. So what I'm saying is, that these objects, including all twists, they generate SH infinite or SH eta, but these pro versions, they are not Pro-list and pro-eta. They are not geometrically generated because there we have these weakly smooth generators, and there's no reason for them to collapse. In fact, they don't. So, okay, that's just a sort of a condition that we don't get objects which come out of nowhere in the sense of not coming from geometry. And so what I will try to say eventually, so let me say what the goal is. I mean, the goal is under assumptions on D and on the scheme on base scheme S. Under certain assumptions that I will gradually unveil, we hope to say deconstructible of some X is the same as D geometric of X is also the same as D X compact. Yeah, so we want to say being compact, which is this categorical finiteness condition, is equivalent to being partition-wise dualizable, or also equivalent to coming from a geometry. Okay, that's where we are kind of trying to go. And in order to do that, we will have to impose certain adjectives on this D especially. So it's basically two kinds of inputs. There is a certain, on top of all these, we have a general six-point formula, so we have these conditions of Constructibility, localization, homotopy invariance. Okay, that's one thing, but we need a little bit more in order to go through here. So we will need a so-called finitariness assumption, which is a certain compatibility with convex, which I will explain. And depending on the situation, also so-called absolute purity, which is another condition, which again are satisfied in many cases. And we will need an assumption on the S, which is resolution of singularities appropriately adapted to what exactly the D is. Yeah, so it's a little bit, somehow keeping several assumptions in place. So I'll try to explain it reasonably clearly, hopefully. So it makes sense. Yeah, so maybe before I go into the discussion and we sort of get lost in the woods, all these conditions that I will ever mention hold, for example, for when D is SH eta motives with Q coefficients over a reasonably nice base field. So sort of if you get lost in all these conditions, that's what you should have in mind is always working. Okay, good. So now I have to start introducing adjectives. This first thing is the so-called finitariness, which is also called continuity sometimes. So the definition is very simple. So we look at a general functor f from PCQS schemes to some target category, or rather, I want to do pop. So the f, let me find this. So this is called finitarian. This is called finitarian. So there's no the term finitary appears in the work of Akio Nephew, but the definition is something very simple. Namely, if what? If the colimit of f of x alpha is isomorphic to D and to F of the limit of the X alpha where where X alpha is the pro object of schemes, such schemes with affine transitions. Yeah, so the case that you want to have in mind here is the one case that could happen so is that these X alphas are open in some X, let's say, in some scheme X, so you take smaller and smaller opens, and then the limit would be let's say if the X irreducible would be the spectrum of the function. Yeah, so this is kind of an example. So you generally want that for all kinds of such affine things. So what is one way to understand this before I go into examples? So there's very nice way of remembering what QCQS schemes are if you want. So remark. So this is called the theory approximation. This technique here. It's the following. So we have again this pro category of schemes, and this superscript here means the transition maps are F1 like before. And I want to look at S schemes, and here I want to do finite type. And here the S is an Ethereum base scheme, so one of our friends. So if we look at these pro objects with affine transition maps, if we ever have such a thing, then we can take like here the limit, and for EGA we know this is a scheme. Yeah, so this limit exists in first place within schemes. Okay. So what else do we know? So we know that it's actually a Q. It's first of all an S scheme for sure, but also it's not only that, it's a QCQS scheme. And this functor is yeah. So this is characterizing the QCQS scheme or some Ethereum scheme as basically a pro category with this little conditional on the transition maps. So in other words, when we ask such a function to preserve these or to send these limits to columns like this, it tells us finitary F is finitary even only if it's time extended from finite schemes in that way. Yeah. So okay, good. Well, this is nice, but what are other examples? So we want to apply this. Yeah, I mean this definition like it makes sense completely generally. So one example that I think is worth mentioning is that if you take K theory defined as a functor on Pi omega and it's produced for your spectrum, this is finitary. Yeah, I mentioned this here because Monday we talked briefly about these smooth non-commutative schemes, which were, well, there was an extra mod blah blah in front, but then independently of that, there was the condition of being contact, which I put. And so K theory being finitary means exactly it's kind of extended from these convex objects in there. And so yeah, that's sort of motivating why we looked at that in the first place. But anyway, that's not completely central for today, but the following examples are worth mentioning maybe more closely. So now we want to apply this to F being some such function formula. Okay? So the functor X goes to D cons of X random. So by this here I mean the D cons like in the classic sense, yeah, constructible sheaves, sheaves, with lambda coefficients. This is finitary if lambda is finite. Right? So in other words, if you really talk about classical orthogonal sheaves, then constructible sheaves are finitary. So this appears in the paper by Matthew and Clausen, Matthew. They showed this. But it relates also to something that I will say in a moment. So for with total coefficients, this condition is satisfied. However, if you do d cons x et al with, for example, QL coefficients, is not finite. Okay, so that's not finitary. Why not? So let's give an explicit example why this is not finitary. Namely, I say, let's say spec fp bar. This is the limit of the spec of these fq's, right? And so being finitary will mean that we can look at this co-limit of the cons of all these spec fq's with QL coefficients. For some reason, there's an omega here, which makes no sense really, but anyway, that's what I want. This would map to the cons of FQ QL. Okay, fine. And so I'm telling you this is not an equivalence. Why not? Well, let's look at the hearts only, only at the being categories, just to simplify. So then here we have just QL vector spaces, right? And here we have, every of these terms here individually is continuous representations of the Galois group of FQ on finite dimensional QL vector spaces. And if I don't pass it higher than that, I would have to talk about spaces. So that's what we have here. And so now the thing is, if this wasn't equivalent, it would tell us, given any such continuous representation, after passing to a finite extension, it's such that the representation is trivial. So in other words, it would factor through a finite quotient of the Galois group. Yeah? So that's not the case. Not every UL rep of Z hat factors through some finite quotient. Yeah, so that's what this would amount to, but that's not. Whereas it is true for finite quotients, yeah, because then it's discrete, and then the continuity of the representation forces you to factor over a finite quotient. Okay, so there is, so in other words, this, whenever you see the word finitary later on, you will have to discard all hopes of applying it to condensed coefficients, basically. But on the bright side, we have that SH et al. And SH is which they are finitary. So, lots of examples, or say lemma, SH, X mapping to SH Motivic, or et al. Of X. So I regard this as a counter from schemes, or like a QSN to PRL stable. Wait, stability doesn't really matter, but anyway, this is finitary. Yeah, it would again not be finitary for these pro versions. So why is that? So this lemma as such, it wasn't known before, but there's a nice write-up of this in this paper by Besani. So the point is that just every one of these steps that appear in the definition is finitary in some sense. And so the function sending x to the category smooth schemes over x. So if you wish to define from schemes to categories, this is finitary. Yeah, so what I'm saying here is if your x is the limit of certain x alphas, and this X is smooth over something else, then there is a finite stage in that limit where it was already smooth. Yeah, so that's the statement here. So the notes there is a reference if you want to check it out. So that's finitary, and so that's the first step, and then sort of sending the category C to three sheaves and C the wedge function from categories to PRL. That's also finitary because it's, I mean, up to these set theoretical questions, it's a left adjoint, right? Or if you wish by Leon's property. So that's also finitary. And the other, and then we have the Misnevich and the Italian topology. They are finitary in the sense that sort of covers are, you know, there are fairly many elements in any cover only, and so that's also finitary thing. And then use it here, this stabilization sending some category C to C adjoint some tensor inverse is also finitary. So every one of these steps preserves, well, let's say, sends co-filtered limits to coordinates, like requested to. Yeah. So that is that's good, and that relates also to this theorem by Charles and Matthew, because yeah, sort of we have talked about this rigidity which tells us under good conditions on the ground, basically this SH et al. With torque degrees is closely related to this. Yeah, so there is a relation between these results. Okay, so that's the condition that we needed for the D, and then there's another condition that we need to impose on the schemes. And so I'm trying to say this without spending too much talk, but it's a little bit tricky. You have maybe never seen it before. So as our base scheme, so I remind you this is in a theorem base scheme. So think of spec K field or spec of Z even or some such thing. Yeah? So that's what we want to consider somehow. And then we say S is, so this is partly here my terminology. So I call the Z resolvable. Maybe I write it like this. So Z resolvable, or it's sometimes called also L prime resolvable, where L prime that is invertible on S, yeah, prime. So L prime means away from L, we will see in a moment. Or then there is separably L prime resolvable, or finally Q resolvable. So what does that mean? So it means the following: if for any, the definition is a little bit technical, but I'll boil it down in a moment for you. So if for any iteration, so this means a proper generically finite surjective map. That's what iteration means. So, for example, a blow-up would be an example of this. But you may also find extension of the function field for it to be an iteration. So, if for any iteration S prime over S, and any nowhere that's Z in this S prime, you can resolve this S prime basically in a specific sense. So so for any S prime basically, I mean, ignore this D for if you wish for a moment. So the condition now is there is a projective map from S double prime to S prime such that S double prime is regular. Okay, so that's the resolution aspect. And then there is it's useful to carry around with you the possibility of looking at a certain z here. So the condition is that the pre-limit of z is a strict normal crossing divisor. So it's a union of smooth things which intersect also into smooth things. And now, yeah, there's obvious thing missing. So what is the condition on the F here? Depending on these four cases where P is. So now Z resolvable is meant to, so this is the strongest condition, this is a little bit weaker. Well, okay, no, I should put it. So that's a little weaker, that's still weaker, and that's the weakest. And so the weakness that you allow yourself is what happens generically. So in the first case, you ask P is generically an isomorphism. Yeah, so on some open, you want really to be an isomorphism. So like for blah, blah, that would be Z resolvable. Prime resolvable means that generically and this is so generically how to write K of as double prime the extensions here of that you have generically is finite of degree prime to this fixed number L. So that's what L prime resolvable. So this prime means away from L, yeah. And separate, this adjective separately means this here plus not just finite, but finite and separable. Okay. And finally, Q resolvable means just finite. Yeah. So this is the strongest condition here. You don't allow yourself any modifications in terms of changing the function field. Here you allow yourself to do a finite separable extension. Here you allow here you allow yourself a finite separable extension of a certain degree prime to that fixed number L. And here you forget about separability, and here you just forget about any constraints on matrix. So now this looks like devil is nailed up. It's actually appearing as such in this work of BUC as Notari on what's called Holy Cover. So that's where that's I think the most definitive source on that right now. So this is the definition. Now what is the theorem? The theorem, which is of course Hironaka, in versus 0, I will write it down in a moment, and then the Young. And then there is additional, so the Young kind of is responsible for this last thing, and then Gabor had the idea of, or the ability of refining this. So Gabor and some marks due to Temkin. So what is the result here? The result is the following. So my notation is again S is as before, and X over S is a finite type. And now, yeah, these people prove that this condition are actually satisfied. So you can resolve the singularities. So let me try and state it as follows. So if S is set K characteristic 0, if you have characteristic 0, then any X like this is resolvable. Yeah, so in other words, in particular, if you apply this to to S itself, then this is telling you you're going to X itself, sorry, then you're going to find a projected map which is generically an isomorphism, and so that the top is regular. Okay, so that's Fibonacci. Plus, yeah, some. So this Temkin here is responsible for pushing this further to not just finite time maps, but I think maybe there. So yeah, Temkin, let me say this. Any there is some adjectively unnecessary quasi-excellent scheme in characteristic 0 if also resolvable. So this is here working. Now if S is the field of characteristic P, positive characteristic, then X still of finite type over my ground field now is separately L prime resolvable for any L or any prime other than the characteristic. Yeah. So you pick yourself some prime that you want to avoid. So let's say P is 2, and then you can say all other primes other than 2 you can. So you fix yourself one of those. So let's say 7, and then you will be able to find a resolution of singularities so that that generically it's a separable map, and the degree of that extension is prime to 7. Yeah? So it's a little bit kind of tricky to navigate, but sort of what you cannot avoid, that's the after of all this definition and theorem together. In characteristic P, you will not be able to avoid extensions. I mean, according to current knowledge, you will not be able to avoid extensions of degree P in the process of resolving. Okay, that's what happens over here. And then finally, if S is quasi-excellent and of dimension at most 2, if your base scheme is very nice, which I think is a very nice condition, then any X of finite type is Q resolvable. Yeah, so for example, if S is state Z, then you have to accept general finite extensions of the function fields that show up. Okay. Good. So all right. Now, so of course that is the massive theorem. Yeah, so all what I'm telling you now here is kind of kindergarten in compared to that, but anyway, luckily we have that. So what does this buy us? It buys us that we have more narrow generators than you might initially think. So here's the proposition. So of course this is going back to I guess Ayub again, and then it has been kind of revisited and massaged a little bit over time. So in the notes you have some references here. So let me say the following. So again, let S be Euclidean. And now I want to also define a dimensional because we're going to do inductive dimension in a moment. And D a functor, 6 functor formalism on UCQS schemes over S. And so I guess we want to have forward probability for finite type S, like we have for SH. So this is the 6 functor formalism, and now we have proposed a few conditions. So yeah, first of all, yeah, okay, let me say this, and maybe now I want to order it as follows. So we say we assume so D is finitary. Okay, so once again, it turns filtered limits into colimits. Then it is geometrically generated, which means that all the objects come from geometry of F03 ground star for finite mass. And I also want localization. And I also want that proper maps are prim. Yeah, all these conditions we know we hold for SH, or as a SH's image. Okay, so these are kind of, and now we have to kind of combine the assumptions kind of related to the singularities and this D here. And so this is So let me try to write it down as follows. So we will do three cases, A, B, C. So we assume S is either resolvable, which in practice means, characteristic 0, or separately prime resolvable, which in practice means you are over a field of characteristic, positive characteristic, or Q resolvable, which once again means you are over Z, for example. So we assume this, and then depending on that thing, we say, I want to say lambda is the sphere spectrum, or here I want to say lambda is Z1 over L, and here in this case I want to say lambda is Q. And so why does this lambda come up? So and then we want to say D is lambda linear, by which I mean it's actually not a functor to PRL, rather it's a functor from D takes values in lambda linear categories. Yeah, so by which I mean modules over, if you wish, mod lambda in spectra in PRL state. Yeah, so depending on how strong the resolution of singularities is, the weaker the resolution properties are, the more assumptions you have to put on it. So the more important you have to kill this. Yeah. Okay. So this assumption, I hope it makes sense to you. So let's again. This is kind of the boilerplate, if you wish. So this applies to XH et al. And SH Motivic, for example. And this is how you combine resolution singularities and impose some condition on D. And now what's the conclusion? The conclusion is that this category is generated, like I said, by a more narrow set of objects. Sorry, there's still something missing, I apologize. And we assume that in case, so for B and C, we assume the following. So the 1 goes to pi low star pi alpha star 1 is split for any, so phi is in that from spec, my notation here is spec L to spec K. This is always a field extension, and here it's a separable finite extension of degree, again, prime to L. Let's say I write, degree prime to L, and here in this case, C in this durable will just any finite extension. I will comment on this in a moment. This will also be very often satisfied. I mean, it's conditioned, but you will see in a moment. Okay, whatever. So what is now the conclusion? Then this D of S or D of X, and D of X is generated by, so I remind you, D of X being generated meant it is generated by F lower street of 1 for finite tab maps, and now it's still F lower street 1 twist n, but now for F being proper, for F, let's say T to X proper, and this source T is regular. Okay, that's the generated subkeys. Okay, so there's two exponentials: the properness and the regularity. Okay, good. All right, that's the statement, and I want to, should I have only half an hour left? Yeah. Wow. Oh. That's unfortunate. Yeah, that's really unfortunate because I was so happy to Okay, I will. I think I will just say a few words orally about the proof. That's no, I can't. I mean, I do want to say where this condition here comes from. Okay, so let me. So you have the notes in front of you, so you are willing to look at them. But I want to comment on where this thing comes from and where the finitary comes from. So proof lines, let's say. So there is a bunch of boilerplate reduction steps. So you reduce yourself to this T being reduced to being integral by some dimension count and so on. So there is a bunch of reduction steps, and then you eventually reduce to the case when this T is already proper. The T over X is proper for the purpose of the argument. Now we are trying to show that for such a general random proper thing, we can express the motive or the Borel-Moon motive rather of that property in terms of something where it's also regular. So of course now here we now use this resolution of singularities. So this will be a regular scheme now. Yeah, so resolution by this resolvability. And this will be a projected map. Okay. So the T prime is still regular, is still projected over my base, but also now regular, and now in Hironaka you would know, okay, generality is an isomorphism, and De Jong and Ngara and so on, they tell you something weaker. They tell you that if you have this generality here, this is a finite and or separable and or conditions on the degree. Yeah? So this finite thing here corresponds to exactly these assumptions. Okay. All right. And so let's call this maybe P prime. And so of course now this will have some function fields. So here's K of U, stack of K of U, stack of K of U prime. So this is now this finite field extension that I mentioned there. And so we ask for a splitting of this map there. And so that splitting buys you that, so first of all, by this finitariness, the splitting of this, so this would be this phi here, the splitting of one mapping to phi no star one. So this exists by assumption, okay, and then by finitariness, this, so that one was one here, next looks like K. And then you have one on U mapping to P prime no star 1. So again, by finitariness, this splitting will extend to a certain open neighborhood of generic point. And that buys you that you can somehow say, well, you can kind of trade off the moral movement of U in relation to the one of U prime, and so that in the end is kind of relevant. Yeah. So yeah, that's where this condition comes from. And now the question is, where is that condition satisfied here? I mean, the other ones I think I commented on enough, but that extra condition is so I mean it's a star here. This extra condition star is satisfied often, very often. So this holds for SH Misnevich. Well, with this lambda, yeah. So the lambda I will not touch anymore. The lambda we have to accept anyway. And finite separable extensions in characteristic, positive characteristic. So then this is known, and this, I mean, I don't know if there is a really proof just purely axiomatically. So how this is proven is as follows. So now we are talking about endomorphism of the monoidal unit in SH over a field. It's known that endomorphism ring there is the Grothendieck bit group. And then there is a really argument involving quadratic forms that shows this. Yeah? So it's a little bit, we have to go into it quite deeply. And I do think there should be an argument purely in terms of A1 invariance and so on, but at least current literature is offering that. Okay. So the consequence of this is, practically speaking, that if your S is a field, so it's either characteristic 0, in which case you have Fibonacci, so you don't need to conjugate this anyway, or you have positive characteristic, in which case you can apply this. And so then the only sort of condition in the end is that you have to invert. Yeah, so that's a very useful interplay here. So it holds for this. It also holds for KGL modules, KGL to further than that. So there the argument is, I mean, you always have to basically come up with some sort of transfer. Yes, so in that context, now we will be talking about about K theory of some fields, and then the thing is, well, you have the kind of a norm map going back. If you have, so the extension here was called, where is it? KNL, I think. Yeah, here. So here you're tensoring up your kinetic spaces to L. That's what the unit map amounts to, and then you have the forgetful pointer, and so the composite is you multiply with the degree of the extension, yeah, which has been rendered invertible thanks to this lemon. Yeah? So it's working there as well. Again, the notes there are references, and it's also working. So also holds if D is is linear as before and has état descent. Yeah. So if you have état descent, then what's going on is the following. So you have to check this condition here for a finite extension. You can replace it by a Galois extension. And what you then show is that this one is actually isomorphic to the Galois invariance of Philo star one. And that is something you can check out for pullback along that map phi. And then it boils down to the case of the trivial covering several points mapping down to a single point, and then you again see it because the order of the extension has been inverted. Yeah? So there is kind of several ways of going through here, but after this, in practice, this condition is satisfied, and that enables you to get this more narrow set of generators. Okay, so good. Now, what is this all good for? This is what I already have a bunch of strong consequences. And today, anyway, I'm running out of time, but I will start giving consequences for what happens when you are on a field actually. So, let me say corollary. So we say this S and this D are as above. So again, if you go mostly on the assumptions, and S, no, sorry, well, S, so S is spec K, and D is as above. So D could be état motives or Nasseri motives with the characteristic inverted. That's what you should think of. I mean, not the characteristic. I mean, the in case of positive characteristic, you have to invert. Yeah. So anyway, now the state is the following. Then we can say geometric objects are realizable. Okay. And if, in addition, if D is compactly generated, by constructible objects. Naturally, the emphasis being on this compactly here, we already assumed it is generated by constructible objects, but now we want them to be compact on top of it. Then we can kind of close the circle here, and then we can say geometric objects on a field are in fact all the dualizable objects, and that we are also all compact objects. Okay. that's the result here, and this is now really an immediate consequence of the. Sorry, I forgot one word. Maybe I wanted to say. I mean, I said it's a field, but I want it to be perfect field here. And we will talk about that, overcoming this perfectness as well later on. So maybe I'll keep. Yeah, so I will erase all the assumptions because more states. The consequences generate their rate. I think now first. So we know that this TGM geometric objects is generated by F grid 1 is n where this F from T to spec K. So this is regular and therefore smooth. Yeah, so using the perfectness or perfect field, any regular field of finite type is smooth. And this F here is also proper. And so now we have proper and smooth things, and then we can conclude that, I mean, by this probability, these are realizable. And I think, strictly speaking, I have not yet assumed all these. I think I did assume that proper maps are prim, and I still have to assume that that these smooth maps are suave and so on. So maybe I will correct it in the notes. Yeah, so under our usual sort of assumptions. Anyway, so then these are realizable. Okay, that's fine. And so that's telling us this one here. And what about this guy? So now we have to take a realizable object and see how to contend with it. And that's actually a tricky thing. Yeah? So because realizability doesn't give you all that much. So it's kind of a bit of a hack, you can say, that assuming this guarantees you can still control it. So by assumption, now I'm looking at the second statement. So by assumption, the monodic unit is compact. Okay, because I said constructible objects, in particular the unit, are compact, and therefore any dualizable object is compact. Okay, so we get an inclusion from dualizable into compact basically by assuming the monodic unit is compact. And now, what about compact implies geometric? Yeah, so we have B of K omega. This, I want to show this is indeed geometric of K. Why is that? Well, this is because it's basically by assumption, yeah? By assumption again. So because we assumed that D is compactly generated by precisely the geometric object. I wrote constructible. Yeah, okay. Maybe I should have. I mean, it's correct what I wrote, but let me write geometric objects here. Because it's more correct. I mean, constructible in the end will be anyway dualized objects. So let's say geometric objects here, and then the geometric objects are a set of compact generators, and therefore we have two different set of compact generators that are already in all the compact objects and the geometric ones, but then we know this there's up to the passing eigenvalues they have to be at. They have to be equal. Yeah? So the paradigms, you have some category C, and in there you have C1 and C2, which both generate compactly, and then with C1, the eigenvalue completion is the eigenvalue completion of C2, but here we have defined this being geometric as being stable under equivalence. Yeah, so that's why. Okay.
So why is it that since it's compactly generated by geometrics, then all compact objects are geometric?
Yes, exactly. So we have this large category, which is D of K. And we have two subcategories. One is the category of compact objects, and the other one is the category of geometric objects. Okay, so these are both stable and idempotent complete. Okay, so we look one by definition and the other one by the general nonsense. And what I'm saying is, if I have two subcategories of consisting of compact objects, which they both are, yeah, so if let's say they are both in C omega, they're writing like that, okay? And if C1 and C2 generate the entire category C under colimits, then this is true. Okay? Does it make sense?
Yeah.
Yeah. Okay. I mean, if you wish, you can. Yeah, there you go. Good. So basically, sort of, there is one geometrically tricky part, which is this included, and then the rest is kind of a little bit, dancing around the difficulty of understanding relatible objects by saying, luckily we have so many other generators that this works out. So, and notably, I don't know of a good general nonsense criterion describing what relatible objects are. That's one of the tricky open questions for me personally. Okay, anyway, so that's what we have here. And so I should comment on this condition here in the spirit of what I did before. I was trying to say, what does this apply to? So this applies to this case. So remark or fact. So D is compactly generated by D geometric for what? For D being SH infinite. So the reason here is that this infinite topology is you can characterize it by this excision, which is really a finitary type condition. I mean, finitary. It's involving finitely many entry economy at the end of the day, and that's why these knitted sheaves are compactly generated, and then all the other steps they don't kill this property. All the other steps in the formation of SH. So this is basically by descent equals excision. And it's also true for less for more primitive reasons for SH etal, but not always, but if the space scheme S has finite, so let's say SH lambda has finite lambda chronological dimension. Okay, so in this event, this SH, as we define it using sheaves as opposed to hypersheaves, is in fact equivalent to this hypersheaf version, and also that it's compactly generated because there's no converging high enough degrees in some sense. Yeah, so in the notes, yeah, I did put reference. So this is a little bit more tricky, but that's relatively easy. So upshot is under a null assumption on the base, base field here in this case, you can apply it to both Misnevich and etal motives. Okay, and so now, yeah, I still have a little bit of time. I want to elaborate on, for 1 second, or maybe 10 minutes, I'd say, on what I said in this opening school in Essen. Like when I said somehow all this machinery and the node of realized objects can be used to prove statements about homology theories, and that's I think very very cool. Yeah, let me maybe just say corollary. So what I'm saying now here is, so the statement itself is due to Grothendieck. The way that this is the corollary of what I said before is due to Saminsky and Degrees. So what is the statement? So for X over C, now a complex, smooth variety, we have the Delan homology of X. The algebraic Delan homology is isomorphic to let's say the analytic Delan homology. So X analytic is the complex manifold, associated to X, and we have the analytic Delan complex consisting of holomorphic branch forms, and that these are isomorphic. So that was proved accordingly, and so I want to, I'm repeating myself a little bit, but I think it's making sense to include this here, this argument in this paper by Susan Kennedy on the Tower motives. Yeah, which is really, again, you should see this more of an example of a statement rather than the one statement. So the thing is, as you will see in the proof, the fact that this motives category here is generated by generalizable objects, that tells you control any available cohomology theory once you know what happens on the ground fleet. Yeah, so let me try and say something about this here. So we have constructed this Devan cohomology factor. So Rho Devan went from SH. So I'm now applying this whole glory to SH, Nisnevich to be precise. So all the assumptions are satisfied for that. So SH Nisnevich, all of the field, or of C now, goes to mod C. So I remind you this was such that you send X to the Devan complex, the right Devan complex of X over C, and then dualized. Well, maybe modified X, I should say. That's how this was constructed basically. So this functor has an obvious variant, which I call Rho Devan analytic, which sends m of x to, well, to the, if you wish, R gamma of x analytic, omega analytic dual again. So why this here exists for the exact same reason as here. So let me recall briefly. So we construct this functor by using the following properties: homotopy invariance, which is true here for analytic homology because it's, for example, isomorphic homology. So it's homotopy invariant. It has état descent because in the analytic situation this is sort of its état limits are analytically locally isomorphic, so it's fine there. État descent, then the Coué formula, so the Devan homology of x times y has to be the tensor product of 1 of x and y, which is again true here for the analytic context, and finally the computation of the homology of Gm up to the base point, which was 1 dimensional. All of these just carry over and you get the same function. You get a functor in the first place. And all these conditions that I just mentioned are what's called a Weil cohomology theory. So this homotopy invariance, état descent, Coué formula, and this one-dimensionality of the reduced cohomology of Gn. Okay, so that's all very nice. But now, what's the punch? So we have, of course, we have a map from omega x to omega x analytic, maybe, but like that for omega. Let's see. Any right vertical one is also holomorphic, and so therefore passing to duals and taking cohomology, we get a map from Rho Devan to Rho Devan analytic. And this is now a natural transformation of functors from SH of C to mod C. And not only are these random functors, but they are both symmetric monoidal and continuous, currently preserved. Yeah? So that was part of the universal property of SH. If you had a functor that on smooth affine schemes was symmetric monoidal, then under these conditions, it extends to a symmetric monoidal and currently preserving functor. Yeah? So we have this. So they are, these are such nice functors. And so now the claim is, how to say it, maybe I write it as fun L tensor from SHC to, in this case, mod C here. So if I evaluate this such functors at 1 at the monoidal unit, which is the mode of C itself, I claim this is conservative. Conservative, why? Well, this category, and it's not here where we use all this machinery, it was compactly generated by the dualizing objects. Okay, and so the colimit preserving factor has to sort of do nothing to these colimits, so we can, so they are kind of extended from here. And now we are talking about a natural transformation between these categories. So now here every object is dualizable. Again, crucially using this resolution of singularities. That enables us to choose these smooth projective generators at the end of the day. And then there is a little exercise / lemma in the notes, which is really a general fact that if you have a category such as this one, where all objects are dualizable, and you have a natural transformation between symmetrical model functions, then they will be isomorphic as soon as they are isomorphic on the null unit. And so here now in our case, of course, the null unit C, spec C is set to just C, and so therefore you get plus ones. Okay. Good. Yeah. That's what I wanted to say about a little application. And one, oh yeah, time's up, so maybe I'll stop. What we will do next is we will push this further. So for the moment, all the results were really basically, I mean, under complicated assumptions on D and S, we only milked this up to, D on field. So we certainly want to get past that. So we want to show that under, again, reasonable assumptions, there is verticality on these constructible, well, maybe I should point here, on the constructible sheaves. And that's something I still want to do. And then after that, I think I want to talk about nearby cycles and molecular positions. So, okay. All right. More questions? Let's whatever.
A stupid question. We said acid and all this theory work for SH means nearest. Is this also work for DM?
Oh yeah, good question. It does. I mean, all these sort of if you have good question. Just comment on that. So the paradigm is we have some D which is nice. So for example, finitary, etc. And then you look at this, I think I call it A. So A is in D of this ground scheme S, and you look at mod A in D of like that's a Newton's function formalism, and that will inherit all the good properties. So, for example, finitary meant it sent a limit of schemes to a colimit. Why is that true here? Well, this was basically, I mean, this is D of X tensor over D of S with mod A in D of S. Okay, and so now you put a colimit in this variable, it will remain colimit. That was finitary. Then localization, again, localization is just a question whether or not certain, whether you have this co-hyper sequence between J or R, or maybe like the rest. This identity. Okay, so let's say this works out in your D. If you want to know does it work out in modules, then the answer is yes, because by this, because I know star has to have this projection formula for this first map, which does because it has localization, and then you tensor it up with the identity of this factor, and you still get the same. Sort of the alien functions are basically the old ones tensor the identity all over this, so nothing changes. So that's localization. And similarly for the other conditions, like this primness is so asking for certain functions to be adjoint, but you basically just say, okay, whatever adjunctions I have, I tensor them with the identity on something and it remains an adjunction. So roughly that's the one sentence answer to why it works. So the answer is yes. Good. I should have said it. So I'll put it in the notes at least.
And the last series you just cleaned it, that series just is really useful for identify like two realizations they are equivalent on the just to look at the identity. That's
Yes, yeah. So if you have, I mean, it doesn't apply to every realization. So the key thing is it has to be a tensor functor. Yeah. So for example, this is true for the Lamp homology and for, let's say, as an example, also analytic homology over a field, but there are others such as absolute logical homology or the homology or things like this, where you have finer structure. Yeah? So it's not necessarily always not any interesting realization partner has that property, but if they do, and if they agree on the motive of the ground field somehow, if the coefficient ring, if you like, is correct, then yes, they have to be isomorphic cubes.
So, for example, the people think, like, for example, the RAM analytic, the RAM realization should be equivalent as AT realization.
Yes.
Starting really fast.
Yeah, for example, I mean, you could put H Betty or maybe put C here.
Yeah.
And then, yeah, I mean, in some sense, I have already used the comparison of this with Betty for giving a hand wave argument while this is totally invariant and so on. But I think you could probably sidestep that. I'm not sure what's the best way, but yeah. But in any case, the answer is yes, yeah.